In this video, we're going to learn how to write the equation of a line in 3 space. So thinking back to 2 dimensions to begin, in 2 space, the equation of a line can be written from either knowing a point and a slope, or 2 points. And from those 2 points, we could use the slope formula, and then we have a point and a slope. And we had 2 ways to write the equation of a line in 2 dimensions, and that was either slope-intercept form or point-slope form. Both of those required slope. Unfortunately, when we add the 3rd dimension in, we no longer have the idea of slope. So we're going to have to use a different tool to define the equation of a line in 3 space compared to the way we defined a line in 2 space. So in 3 space, the equation of a line can be written from either knowing a point and a vector parallel to the line, or 2 points still, since a vector can be created from the points. So now in 3 space, instead of the concept of slope being how we define a line, we're going to use a vector to give us the direction of the line, and we'll still need a point that's on the line to help us define the equation. So there are 3 different ways that we can write the equation of a line in 3 space. So if we look at our diagram, we have our x, y, and z axes, and we have line L drawn in 3 space. Okay, so we need a point, so let's call this point x naught, y naught, z naught. Right, so that's some point that we know on the line. So we can draw a vector to that point, and we'll call that vector r naught. Right, we typically use r for a position in space. Okay, so r naught defines a vector that goes from the origin to this point that we know on the line, x naught, y naught, z naught. And then we need a vector that indicates the direction of the line. Okay, so we need some vector that is parallel to the line. And I drew the vector on the line. As we learned, vectors aren't fixed in space, so it really can be anywhere. But let's call that vector d. Okay, so d will define as the direction vector. And when we get into writing these out, let's write d as A, B, C as the components. Just keep it simple. Okay, so we need to create a way to define every point on this line. So with vector addition, we can do r naught plus d. That would define from the origin to this point here. Or we can add 2 direction vectors from the origin. Now we've defined this point. We can add a 3rd direction vector. We'll go from the origin, right? We could add half of the direction vector. So we have to come up with a way to write an infinite number of vector additions, right? Because there's an infinite number of points on the line. So there's an infinite number of vector additions that we would need to define for each point. And for instance, let's just draw one of these in. So here we'll have vector r of t. And t is some scalar, how many times we use the direction vector, right? So this would be r of 2, let's say. So it's r sub naught plus 2 direction vectors. Okay, so generalizing this idea, we can say that the vector equation of a line would be r of t equals r naught, that first point we knew on the line, plus some scalar of our direction vector. So we'll use t as our scalar and d as the direction vector. So t equals a scalar. All right, so we've written a general vector addition expression to represent the way we would define every point on the line. So writing it out a little bit differently, but still in vector form, this would be r naught, so x naught, y naught, z naught, plus t times the vector a, b, c. So x naught, y naught, z naught, plus t times that direction vector of a, b, c. And instead of writing it as two separate vectors, we can combine into a single vector. So x naught plus at, y naught plus bt, z naught plus ct. Right, so there's our vector equation of the line, a general vector addition equation. Now we can write the line parametrically. So that's as simple as taking the vector equation and writing the components out as parametric equations. So this first component is the x component. So we'd have x equals x naught plus at, and then y equals y naught plus bt, and z equals z naught plus ct. Parametric equations are a little bit more familiar to us since we've used them in previous courses compared to the vector equation of the line. But now we have two of the three forms down. Now the last way we can write the equation of the line is a symmetric equation. So simply put, what we're going to try to do, instead of writing them as three separate equations, can we write it as a string of expressions equal to one another? And the way we would do that is to solve each of these parametric equations for t. So if we did that, so we would solve for t, so we'd have x minus x naught divided by a. That would be equal to t in the first equation. And then in the second parametric equation, we'd have y minus y naught divided by b. And then the third one, z minus z naught divided by c. And each of these expressions is equal to t, which means that they are equal to one another. And there we have our symmetric equation for the line L in 3 space. Now, if one of our equations does not have a t in it, which can happen, we might have, let's say, x minus x naught over a equals y minus y naught over b, comma, z equals 2. Right? So if there's no t, then we just include that part separately. It stays basically like a parametric equation, and we just write the other two parts symmetrically. Okay, so these are the 3 ways that we could be asked to write the equation of a line, or we could be given the equation of a line in 3 space, all based off that vector addition again. And this piece, the direction vector, now taking the place of what we knew as slope in 2 dimensions. So find parametric equations of the line through the points 2, 1, 4, and 3, negative 1, 5. So in this example, they're starting us off with 2 points. So we need a point and a direction vector. So let's use the points to define the direction vector. Now here, because we have scalars that will be positive and negative, doesn't matter the order, but let's treat 3, negative 1, 5 as the terminal point and 2, 1, 4 as the initial point. So 3 minus 2 is 1, negative 5 minus 1 is negative 6, 1 minus 4 is negative 3. So there's our direction vector. And to write the equation of the line, we need a point and a direction vector. So doesn't matter, let's pick 2, 1, 4, just since it's the first point that they gave us. So parametrically, or first let's go vector, even though they don't ask for it. So r of t would be equal to the vector from the origin to that point, which would just be 2, 1, 4, plus scalar multiples of the direction vector, 1, negative 6, negative 3. So we can write this as a single vector then, and then parametrically, we're just taking each of the components out of the vector equation. So x would be equal to 2 plus t, y equals 1 minus 6t, and z would be equal to 4 minus 3t. So there we have parametric equations for the line through the points 2, 1, 4 and 3, negative 1, 5. Now use the equations to find 2 other points on the line. Okay, so if we made t equals 0, which would be easy, we would get the point 2, 1, 4, which is not a new point. That point's already on the line. If we made t equals 1, also an easy value of t to plug in, we would get 3, negative 5, 1, also a point on the line. So we need to pick other values of t besides 0 or 1. So let's go t equals -1 to start. So that means that the point would be 2 minus 1, so 1. 1 plus 6 now would be 7, and 4 plus 3 would be 7. Or we could say t equals 2, and we would have 4, 1 minus 12, so -11, and 4 minus 6, so -2. And I picked integer values of t. Doesn't have to be integer values. We could have picked t to be 0.5 or 1.5. Doesn't matter. All of those values of t are covered to define the infinite number of points on the line. So then they ask, can this line be defined using other sets of parametric equations? So the answer to this is yes. There's not one single set of parametric equations that work to define this line. We could use other points, right? We could even use the 3, -5, 1, which we didn't use to define the parametric equations, or we can use different vectors. So vectors parallel to the direction vector, right? The direction vector just gives us a direction that the line is going in. So in this case, that direction vector we found was 1, -6, -3. If we wanted to, we could use 2, -12, -6, right? That would change the t values. That would give us the points that we found, but we'd still be able to find these points. It would just be a scalar multiple of the direction vector, and it would still define the equation of the line. So there are an infinite number of parametric equations that we could write to represent this line. Find a vector equation of the line through the point 0, -4, 8 that is parallel to the vector 2i plus 3j minus k. So if it's parallel to this vector, we're going to use this vector as our direction vector. So then r of t, the vector equation, from the origin to the point, would give us the vector 0, -4, 8, plus scalar multiples of the direction vector 2, 3, -1. If we'd like to write that as just one vector quantity, that would be 2t, -4 plus 3t, 8 minus t. All right, there's our vector equation. Find symmetric equations of the line through the point -1, 5, 2 that is parallel to the line x equals 3t plus 1, y equals t, and z equals 4 minus 7t. Okay, so if they're parallel, we can use the same direction vector. So the direction vector of the line that they gave us is the coefficients of t, right? The coefficients of the scalar give us the direction vector. So that's 3, 1, -7. So there's our direction vector. We are given a new point to go through. So symmetric equations, so let's write them parametrically. I'm going to do that without writing the vector equation this time. So x equals -1, the point, plus t times the direction vector. Lost that word for a second. So x equals -1 plus 3t. Y equals 5 plus t. Z equals 2 minus 7t. And if we're going for the symmetric equations, we need to solve each of these for t. So in the first parametric equation, we'd have x plus 1 over 3. Second equation, we'd have y minus 5. The third equation, z minus 2 divided by -7. Since all of those expressions are equal to t, they will be equal to one another. And there we have our set of symmetric equations that represent the line based on the information that they gave us. Okay, so we wrote parametric, vector, symmetric. Symmetric is probably the one we use the least, but we have to get equally as comfortable because when we're presented with a problem, they could really use any of the forms for the equation of a line in 3 space. When comparing two lines in 3 space, they can be, okay, so let's step back for a second. In 2 dimensions, if you draw 2 lines, there are 2 outcomes. Either those lines intersect or those lines are parallel, Or I guess the third one would be the lines are the same, which is true in 3 space as well. But let's focus on the cases where the lines are not the same. So if the direction vectors are scalar multiples, that means the 2 lines are parallel. And lines being the same technically fall into the parallel case anyway. The second case, there's a specific t and s such that the lines intersect at the same point. So that means the 2 lines will be intersecting. Okay, so all this means is there's a scalar for each line, t for one line, s for the other, just to differentiate between the scalars. Realize they're not the same. There's a scalar t and s that you plug into the first equation, you plug into the second equation, you're going to get the same point. So that means the lines are intersecting. And then the third, lines that are not parallel and do not intersect, we call skew. Okay, so if we want to draw out what this looks like, parallel, simply put, just draw parallel lines. 2 space, 3 space, they're going to look the same. Intersecting, same idea. And there's our intersecting lines, intersect at a point. Now, skew lines are a little bit harder to draw in 2 dimensions because this case doesn't happen for 2-dimensional lines. So the best way to visualize it is draw 2 parallel planes. So plane 1, plane 2. Those 2 planes are parallel. So skew lines are lines that are in parallel planes but are not parallel lines. So for instance, if I drew that diagonal on the top plane and that diagonal on the bottom plane, they're not parallel lines since I can't take a separate plane and include both of them. They don't intersect because they're contained in parallel planes that never touch. So the last option is this third option that we define, which is called skew. So algebraically, how do we determine whether a set of 2 lines are parallel, intersecting, or skew? Let's look at that. So determine whether the lines L1 and L2 are parallel, skew, or intersecting. If they do intersect, find the point of intersection. Okay, so let's start with the easy one, which is parallel, which means either their direction vectors are scalar multiples of each other or that the cross product of the direction vectors is the 0 vector. I'll take the first definition, it's just easier to check. So for the first line, the direction vector is -1, 3, -4. And for the second line, the direction vector is 2, -4, 1. Okay, so comparing the x's, the scalar would have to be -2. But then comparing the y's, we could see that that's not the case. Okay, so that means not parallel. Right? Direction vectors are not scalar multiples. So now let's work under the assumption that they do intersect, and at the last minute we'll be able to decide between intersecting and skew. So if they do intersect, that means the x values would be the same, the y values would be the same, and the z values would be the same. Now we really only need a system of 2 equations since there are 2 unknowns, s and t, so let's just stick with the x's and y's for no other reason than they come first. So we're under the assumption that the x's are equal and the y's are equal. So that means that 3 minus t equals 8 plus 2s, and that 5 plus 3t equals -6 minus 4s. Okay, so we have a system of 2 equations, 2 unknowns. So if we solve the first equation for t, so that's going to be -t equals 5 plus 2s, t equals -5 minus 2s. We'll substitute that in. So 5 plus 3 times -5 minus 2s, -6 minus 4s. So 5 minus 15 minus 6s equals -6 minus 4s. So -10, add 6, so -4, add the -6 over, so 2s, so -2 is s, and t then is -1. Okay, so we found the s and the t value that make x's equal, y's equal. So to differentiate between whether these are intersecting or skew, we have to compare the third coordinate, which we didn't use in our system. Okay, so we're going to compare the z. So for L1, z is equal to -1 plus 4, so z is equal to 3. For L2, z is also equal to 3. So we worked on the assumption that x and y were the same. We showed that z is the same, so that means that these lines intersect. And they did ask for the point of intersection. So that means that we need to take either t equals -1 and plug it into the first line, or take s equals -2, plug it into the second line. Doesn't matter, since it'll give you the same point. So going to the first one, that means that we get x to be 4, y to be 2, and then we already know z is 3. So they intersect at 4, 2, 3. Okay, try this one on your own. So pause the video, go through the steps, play it, see how you did, and then there's one more left to finish off the video. Okay, so hopefully you found that these lines were skew. If we compare the direction vectors quickly of 1, -2, 12, and 2, 1, -3, not parallel. In my work, I set x's and y's equal again, so 4 plus t equals 3 plus 2s, and -8 minus 2t equals -1 plus s. Without showing my work, I found that t was equal to -3 and s was equal to -1. And when I went to compare the z values, for L1, z was equal to -36, and for L2, z was equal to 0. So x and y were the same, but the z's were different, so that means that these are skew. Now, what also might happen for skew lines is you might set up this system of equations for x and y, and you find that the system has no solution. That would be another indication that the lines that we're comparing are skew. Okay, so we can come to this conclusion in a few different ways algebraically. It's just important to pick up on what's happening and what the conclusion of that is. So the last example, nice easy way to finish it. We have lines in symmetric form. So for L1, the direction vector is 6, 2, -8. For L2, the direction vector is -3, -1, 4. So if we compare, we see that D1 is equal to -2 times D2, which means these direction vectors are scalar multiples. That means that these lines are parallel. Okay, so we define the equation of a line in three space in three ways: vector, parametric, and symmetric. We answered a few questions using those different forms of the line. And then we talked about how lines can relate to one another in three space, being parallel, intersecting, or skew, and how to check that algebraically. Right? Going to be important to practice this. For lines, you worked a lot for a long period of time in earlier math courses, and now we're really condensing this into a shorter amount of time. So practice is going to be key here.